Hello everyone, I am back again. Today we're going to talk about how reactions actually occur and what happens for a reaction to really occur. So I'm going to jump off to the side so you can copy down some notes, then I'm going to come back and we can talk about it. Alright, I know there's a little bit of a glare, so we'll go through it and I'll kind of explain about it, but we're talking about collisions between three or more particles here, and for a successful collision. I understand some of those are a little bit hard to read, and I apologize, but this is kind of the best lighting setup I can get. It gives me enough light to make these videos, but unfortunately it's a little bit too much, so it's a little bit washed out in some places, but it's kind of the best we've got. Okay, so we're going to talk about collision theory here. Now, collision theory, it pretty much states that reactions aren't magical. All right, reactions don't just magically occur between two particles. The particles actually have to collide. They have to be touching each other for the reaction to proceed. Now, remember, reactions are things like forming and breaking of bonds, or the sharing or, I guess, unsharing of electrons. So, for a reaction to occur, for two atoms to share electrons, they actually have to, the electron clouds have to overlap a little bit, and those electrons can then move between the two atoms. So they have to be touching. All right, reactions don't proceed when the two atoms are way out here. They have to actually touch. The electron clouds have to overlap. And let's say you need a double bond or a triple bond, they have to overlap even more. Now, it's only occur when they collide. But the thing is, atoms don't know anything, they don't think anything, they don't feel anything. They just do. And what atoms do is they kind of float around or fly around randomly. So let's say we have a beaker and I want a reaction to proceed. Those atoms have to hit each other, but at the same time, they're just moving randomly. All right? For a reaction to proceed, they have to collide. Well, it's going to be not tricky, but it's most of the time reactions are between one particle just breaking apart or two particles colliding. Very rarely do you have three particles because they have to all instantly collide at the exact same moment in the exact orientation, and they all have to have the same amount of or enough energy. And that's kind of rare. That doesn't really happen very much. And when it does, it happens slowly, meaning let's say 1 out of 100 collisions results in a reaction. Well, what we would see then is a very slow rate of reaction, right? Because 99 collisions occur first, and then we get one. Then another 99, and then we get one. And I understand it's not how statistics work, but bear with me. Whereas if it's 2, well, it's a lot easier because all that has to happen is they have to hit, and boom, you got a reaction. Whereas the other one, you got to have these two, and then the third one has to come in, and they all have to hit at the exact same moment. It just doesn't happen very well, very often, and as a result, you just don't generally get that to happen. And when it does, it's a very slow reaction. All right? So, for a successful reaction to occur, the particles need to collide, and they need to have the proper orientation, meaning that particle A has to collide with particle B at the right spot, and they both have to have enough activation energy, or enough energy to overcome the activation energy barrier. And we'll talk about that next time a little bit. But what it's essentially saying is when I have these particles colliding, they need to have enough energy, meaning that they need, if they don't have enough energy, the electron clouds kind of bump off and they kind of repel each other before they really get that good overlap that they need. They need enough energy, which usually is thermal energy, which is speed. So they need enough speed to collide and then react. So get that overlapping of the electron clouds so they can react and they can form a bond. But that being said, you know, if you have, remember we talked about sigma bonds and pi bonds, if you have these colliding and the orbitals don't overlap because orbitals are shaped, it's not just a sphere, there's shapes to them, if my orbitals don't overlap, they'll just kind of bounce off of each other. So they might have enough energy, but if the orbitals aren't overlapping correctly, they'll bounce off each other. Or they might align correctly, but if they don't have enough energy, they won't even get close enough and they'll just repel each other. So there's a lot going on in a reaction. And that means that generally, it's a series of steps. Okay, it's not just one thing, right? When we talk about a reaction, oh, here it is. Right, we always talk about the classic reaction of oxygen gas turning into water vapor. Oxygen and hydrogen turning into water vapor. Well, we just said that three particles are rare and very slow. This is not a slow reaction. All right, this is a very, very explosive reaction. It used to be used as rocket fuel in the early days, so it's a very explosive reaction. It's a very fast reaction, meaning that this is just the overall reaction. This actually occurs in a series of steps, in intermediate steps, but we just don't show that because we try and simplify it. Well, now you're in AP chemistry, now you're in big boy and big girl chemistry, now we care about those steps, and we're going to start talking about those steps, and we're going to start figuring out how we can determine those steps. All right, so there's a lot kind of going on, there's a lot we're going to be working with, but this is kind of the overall general idea that, first off, in order for particles to react and atoms to react, they have to collide. They have to collide with the proper orientation, they have to collide with the proper geometry. So there's two things that they have to collide with. And the more atoms that have to collide that way, the slower and less likely the reaction is to proceed. So one atom just breaking apart, okay, that's going to happen. Two atoms colliding, not a big deal. Won't happen every single time. A lot of times they'll bounce off each other and they won't react. Three, pretty rare, pretty slow. Now you have to have three collide with the exact orientation. They all have to have the same energy. Usually doesn't happen. Four or more, it's pretty unheard of. That's going to be a very, very slow reaction because, not that the particles are moving slowly, but it's just that most of the time they'll collide and bounce right off because they won't be the proper orientation. And if they are, the likelihood to have four atoms all having enough energy just doesn't really happen very often. All right, so that was a brief overview. We're going to talk about how to speed up reactions, so how to increase primarily the energy and to a much smaller extent the orientation. Orientation is difficult because atoms just kind of randomly bounce around. So we can't really change the orientation, but we can change the frequency at which they bounce, which will help. But that's a small effect compared to the activation energy that we can affect. So that's going to be the next video. All right, I will see you in class.